Okay, let's start. Welcome back after our prize holiday. Um, as you can see from the announcement there, I had already posted the test grades. This was on Saturday, I think. Posted the test grades and also posted the test answers on Blackboard. So the test answers are there, but I'll give you your test back now. If you haven't seen that yet. Everyone so far. Okay. So the of course now that's in the grade book, right? Your average is updated, so whatever you see under my total there, that's your current average. And then I also added to your flux dollars. So if you want to look for those, um, you can. So I think the grade book is pretty much um, up to date at the moment. Of course, we'll have another homework here coming in, this homework on Extrema, and then kind of a differentiation because we've already started talking about integration, right? Um, I wanted to, so we still have a few sample problems from Extrema that we didn't finish, although we had already started talking about integration. And so I want to finish some of those examples on Extrema because they're um, maybe some of the more interesting examples. And then we'll continue talking about integrated integrals, also usually known as double integrals, in particular, what um, double integrals mean, right? So last time we were computing them, this was for the test. We were computing, but we hadn't discussed. Uh, the last time, way before the test, we probably already um, but we were starting talking about double integrals, but and how to compute them, which is one thing, but then what they actually do for us, right? What their significance is, that we really hadn't gotten into. Today we're going to give a simple application of double integrals, but not really a useful one. but at least it will start giving us some justification for doing double integrals. But then we're going to get into the real important applications of double integrals. But those important applications are going to be conceptually more difficult. So So there, those are going to expand our imaginations a little bit, I think, our mathematical imagination some today. So I hope we get to that once we get past the more mundane examples. I wanted to look at just one problem, but there may be other problems that you're interested in here from Extrema, because there's one that says use a computer algebra system, and yeah, it's this one. Okay, so you really can start this without using the a computer algebra system means something like Wolfram Alpha. Okay, some of your calculators have computer algebra systems built into, so those are things that do algebraic manipulations, right, or do sophisticated graphing. Those are computer algebra systems, and but you can really start this problem without using a computer algebra system, but then it gets more challenging. So it says using a computer algebra system to graph the surface and locate the extrema. So that would be if there's any relative minima or relative maxima, or if there are any saddle points. Remember now, though, we have our second derivative tests, right, to help us locate local minima and local maxima or saddle points without having to make the graphs, right? Okay, and so that's those problems are also also brought up in this homework. Okay, but you'll see when you start this problem that the second derivative tests are a little bit awkward here, just because of the nature of this formula. All right, makes those difficult to calculate. So let me let's work on this one and see how far we can get into it. So let me lower the screen here and let me find some paper here that we can work on, because we're definitely going to have to do some work here with this problem. All right, so let me go to the bottom of the notes here. Let me see if I can write down that formula. So it was z was what, minus 4x over, and then x squared plus y squared plus 1. Okay. All right. So when I was practicing this problem, they gave me a slightly different coefficient in the numerator there, so I had minus 8x. So I hope this one will work out as nicely. We'll see what happens here, right? So again, we're looking for, are there relative minima, or the relative maxima, or there saddle points there on the graph of this function. So if you're just doing this analytically by hand, right, without looking for the graph, then of course what you're going to do first here, right, is find the partial derivatives, correct? Okay, so, and that's already hard enough. Let's see. So I'm going to relabel this as instead of z equals, let's also write it as fxy equals. And then let's you don't really need to do that, but I'm just doing that so I can use the modern function notation in calculating the partial derivative with respect to x, right? So let's try calculating that partial derivative. And since we have this quotient here, right, in our formula for the function, I think maybe let's use the quotient rule to find the derivative. Okay, and that's where things start getting messy, right? We have to remember the quotient rule. So remember, the way the quotient rule works, right, I think, is what you're going to take the derivative of the numerator times the denominator. Is that correct first? So we're differentiating here with respect to x. So you would have minus 4 times x squared plus y squared plus 1, right? And then you subtract off, and then you just do that in reverse, right? So you keep the numerator, right, which is minus 4x, and then times the derivative of the denominator. But remember, we're differentiating with respect to x. So when you differentiate that denominator with respect to x, you're just going to get 2x, right? You're just going to apply the power rule to this term. But the derivative of these two terms would be 0 with respect to x, right? So that doesn't work out too bad. Of course, the bad thing about the quotient rule kind of is then in the denominator here, right, you just you take the denominator of the original function formula, right, and you square it. So that does give you, ultimately, they're kind of an ugly expression for the derivative. Well, what can you do, though? It is what it is, right? So let's simplify this a little bit. Let's see what we have here. We have minus 4x squared minus 4y squared minus 4, right? And then here, all of this is going to be, what's all that going to be there? Positive 8x squared? Is that right? And then again, all over this ugly denominator here. And then we do have a couple of like terms we can add together here, right? So it looks like I get 4x squared minus 4y squared minus 4, right? Over the x squared plus y squared plus 1 they're squared. Okay. And of course, what are we going to do with that? Set it to 0, right? Okay. Because we're looking for the critical points, correct? Okay. And we're hoping we'll find some critical points, and then one of those we're thinking will be maybe will be a local maximum or a local minimum, right? Or maybe a saddle point also. Now, let's find the derivative here with respect to, let's find the derivative here with respect to y, okay? And now that's going to be easier though, isn't it? So again, let's try the quotient rule, right? So we have the derivative of the numerator times the denominator, but with respect to y, the derivative of that numerator is going to be 0, okay? So so that makes things look nicer already. So we have 0 times, and then our denominator x squared plus y squared plus 1, right? And then minus the derivative of the, and then minus what keeps the numerator, which is keep that numerator there, right? Which is minus 4x, and then times the derivative of the denominator with respect to y, but that's going to be what, 2y now? Okay, all of this over x squared plus y squared plus 1, right, squared. And again, we're going to set that equal to 0, but we can simplify that a little bit before I set it equal to 0. I'm getting ahead of myself there. Okay, we can simplify that a little bit and get, what is that, 8xy, positive 8xy, over x squared plus y squared plus 1 squared there equal to 0. All right, now here's where things start getting a little bit worse, right? Because now we have to solve those two equations. Now we have to solve those two equations simultaneously, okay? Now look, first things first, though, is let's not make it worse than it is. Here you have a fraction equals 0, and here you have this fraction also equals 0, right? So that can only happen if the numerators are 0. Okay, so you can ignore the denominator here, right? And so you really have a simpler set of equations there. You have 4x squared minus 4y squared minus 4 equals 0, right? And then what, 8 xy equal to 0. Did I leave something? I didn't leave anything off, did I? I took the derivative there, and I don't think so. So we have 8xy there equal to 0, right? Okay. So any suggestions there? What now? Divide by 4 on the first one? Okay, so that's easy, right? So we have what? X squared minus y squared minus 1 equal 0, right? Okay. And then I guess we can also divide by 8, right? So we have what? X times y equal 0, right? So see any solutions there that come to mind? X and y equals 0? No, I don't think so, right? Okay, because why not, Robert? Yeah, because of the minus 1. Yeah, all right. So it works great in this equation, correct? Right? Okay, but unfortunately, in the first equation, not so great, right? Okay, so other ideas there? 1 and 0, right? Okay, so here we're just going kind of by inspection, all right? Okay, just going kind of by inspection. If we have x equal 1 and y equals 0, right? Okay, then we'll get 1 minus 0 minus 1, right? Okay, and that would be 0. And then if y is 0, right, this equation is also going to be 0. Oh, so I do see this as a, I do see that as a critical point, right? There you go. Right. Okay. So -1 and 0 also would work, correct? Okay. Because you would have again 1 squared minus 0 minus 1 there equal to 0. Yeah. Look, that second equation tells you since x times y is 0, right? You know either x is 0 or y has to be 0. Okay. But they cannot be 0 simultaneously, though, right, Robert? Okay, so that's what Robert discovered. All right. But you do know from this equation, x is 0 or y is 0. So if you try y equals 0 in this first equation, right? If you try y being 0 in the first equation, they can't both be 0. We know that. But if you try y being 0 in the first equation, you get x squared minus 1 equals 0. That leads you to these two solutions, right? Okay. See, if y is 0, then in this first equation, you get x squared minus 1 equals 0. And I know you can all solve that. You get x is plus or minus 1. So that leads you to these two solutions. What's your other option? Well, you can try x equals 0, right? So you can plug x equals 0 in here. And then, of course, what equation would that lead to? That would be minus y squared minus 1 equal 0, right? But that means if you shift the minus y squared to the right-hand side, you would get y squared is equal to minus 1. Is that going to happen? No, right? Okay. So x equals 0 does not lead to any solutions. Oh, so there they are. All right. There are your two critical points. All right. So maybe those are minimum. Maybe those are a maximum, right? Okay. And if we did not have a graph, what would then be our next strategy here? Uh, I don't know. You're just comparing between these two, which is yeah, right. Okay. Yeah. But unfortunately, the graph consists of lots of not just these 2 points, right? Okay. So we've got billions and billions of points, right, on the graph. So we cannot just compare the output values for these two. Okay. Maybe ultimately we'll see that that would have worked, right? But I don't think at that point that's a legitimate strategy. Okay. Um, but so what is our actual strategy? Finding D, right? Okay. And that involves finding what? Mixed the second partial derivatives and the mixed partial derivatives, right? So we would have to compute f of fx xx. I mean fxx xy, right? And f sub yy xy, right? and then also f sub xy, xy, right? Ooh, that's really going to be nasty, okay? Because look at what the formulas are for your first derivatives, right? Okay, they are really ugly, right? Okay, and so you're going to have really challenging here um, second partial derivatives, okay? Because the first partial derivatives are complicated expressions, right? Okay, so that's not a very inviting option. That's why the homework is saying, oh, use a computer algebra system. Actually, look at the graph. Okay, so just cheat and take a look at the graph and see what you see around those 2 points. Let's try that then. Okay, and so let me see if I can do this. So over here. Oh, there it is. Okay. So I'm going to use this is that CalcPlot 3D. Okay. I think there's a link to this in your homework. All right. And CalcPlot 3D works really good in this example because their sample function is very close to the function that we're trying to graph. So we can edit this one pretty easily if I can do that here with my finger. It may be easier said than done. So I want what was it? It was minus 4x in the numerator, right? Let me just take that all off and type in minus 4. So it was minus 4x, right? Minus 4x. Did I do that right? And in the bottom, it was almost the same here, right? Except you didn't have the e, thank goodness, there, right? You just had x squared plus y squared. Was it plus 1? Right? So I can edit this one pretty easily. To get my function, and let's see if it will graph it. Oh, so it does graph it nicely. Oh, all right. And I do see what appears to be minimum and maximum there, right? Let's see if we can rotate this a little bit. Oh, yeah, so we can rotate that. I may not ever be able to get it back where I started. But if you rotate it a little bit just by grabbing the image and moving your mouse or your finger around, you do, and you can indeed, right, see that, well, we do have a local minimum, we do have a local maximum, right? Which one is this one? Can we read the axes very well? I think that's -1, right? So that's x equal -1 and y equals 0. So that turned out to be the maximum. And then this one over here, this is x equals 1, y equals 0. That turned out to be the local minimum. Okay. If you just look carefully there at the x-axis, this is x equal 1 above this point. So that's 1, 0. And then this is -1 below this point. So -1, 0 corresponds to the a maximum. Okay. So just like with functions of one variable, right? Sometimes graphs there really are helpful. Okay. All right. So we can see it, right? This was the local minimum. No, that's wrong, right? This was the local maximum, and this one was the local minimum. But now on other problems, of course, you don't have to draw graphs. So you can, on other problems, you don't have to draw graphs. So you can, I can get back to my homework here. Yeah, on other problems, you don't necessarily have to draw graphs. So for instance, problem number 6, right? This is kind of a baby version of using the second derivative test, right? So they're telling you for this function f, which they're not even giving you a formula for f, right? Or graphing that, to use the second information, right, to determine if you have local minimum or a local maximum or saddle point, right, at this given point, and they don't even specify what. Right? But they give you the information, right? You have the second partial respect to x evaluated at that point, you have the second partial y evaluated at that point, right? Second partial, I'm sorry, the mixed partial, right? Also evaluated at this point. So you those two, that value d, right? And sure. 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 Right. So that's the analytical term. Or saddle points, right? So those also come up in this homework as well. There's not that many problems. There's 8 problems. Okay, so do y'all have any, speaking of this homework, do y'all have any questions about it? That was the only one that really occurred to me as being a little bit confusing. Not that the other ones are easy, but a little bit confusing in terms of the instructions. That problem number 5. Okay, so that one was actually due tonight, but I'll postpone it a couple of days. We're not in that big of a rush to turn it in, so you'll still have time to work on. Still have time to work on that one before that's due. If you haven't finished it yet, I don't know how far y'all into working on that. I didn't look. Okay, let's go. Wow, so many pictures today. Well, since we're talking about extreme, let's look at these last 2 examples. So these are also extreme examples. So here they want you to find the absolute extrema, not local, but actually absolute extrema of this function. And but they're going to restrict the domain of this function somewhat. Okay, so they're restricting it to this closed region. Closed region means it's a region in the xy plane that contains the boundary. So it's x is between 0 and pi, including pi, and y is between 0 and 1. So there's the domain that you can use for. There's the school. It's pretty easy to figure out that actually that you're going to have absolute maximum, absolute minimum. Because the fact that x is between 0 and pi and y is between 0 and 1, that means that we product of these two, right? We're going to have to get something that's between 0 and pi, okay? Because y cannot be any more than 1, right? And x cannot be pi, right? So the biggest this product is pi, and then of course the smallest is 0 because maybe x is 0 or maybe y is 0. Product is going to be 0. So that means you're computing the sign of a number between 0 and pi, right? Well, anytime you can sign of a number, you're always going to get like a value between 0. Okay, right? So you know that that this output from this function, the fxy, has to be something between 0 and 1. It may be 0 now, though. It is possible for it to be 0. That will happen if either x or y is 0, correct? Okay, because you'll have sine of 0, which is 0. It would also happen. Wouldn't it also happen if x is 1 and y is? I'm sorry, if x is pi and y is 1, then this product would be pi, and so you would be getting sine of pi, but sine of pi is also 0. Okay? So so it's definitely possible for the output from the function to be 0. It's also possible for the output for the function to be 1. When would that happen? What now? Oh, not pi, but when xy is equal to pi, you have sine of pi, which is 0. Pi over 2, that's right. So when x times y is pi over 2, then you're going to get output here is going to be 1 sine of 2. Oh, so this gives us an improvement of where to look absolute maximum and absolute minimum, right? So so we actually said it, right? We're going to have an absolute minimum where? That's 0, because this formula can never get less than 0, right? But where will it be 0? When x times y is 0, right? Because sine of 0 is 0. So x times y is going to be 0 if x is 0 or y is 0. So you're going to have an absolute minimum of 0, right? Actually, let's write that down. Absolute minimum of 0 when x is 0 or y is 0, because you'll be calculating sine of 0, which is 0, right? Okay. Or what was the other possibility? Elijah, what were you saying? No, not maximum. Let's talk about minimum first. But you're going to have a minimum. One place is where you're computing sine of 0, right? But where else is sine 0? At pi, right? Okay. So that's going to happen when x times y is pi. So, but remember, x has to be between 0 and pi, and y has to be between 0 and 1. So the only way you're going to get this product to be pi is if what? X is pi and y is 1, right? Okay. Oh, so it's this point, right? X is pi and y is 1, right? Because that will also give you sine of pi, which is 0, right? Okay. Oh, so if you look at a picture of the graph, fortunately, there's one staring you in the face, right? All of this is kind of confirmed, right? Here's the graph of this. Here's the graph of this function, sine times x1. Remember, we're only graphing it over this region, right? 0 to 1 on the y-axis, right, and 0 to pi on the x-axis. So we're only including the surface above this region. But notice, right, when x is pi and y is 1, notice the surface comes down to 0. Okay? So you have a minimum here of 0, but you also have a minimum along this, along the x-axis right there, right? And also along the y-axis. Because along the x-axis, y is equal to what? 0, right? Y is equal to 0 on the x-axis, but along the y-axis, x is equal to 0, right? So this surface comes down, right, and touches the xy plane, z equals 0, touches the xy plane right there. It's two axes. Okay, so you have lots of actually places where you have an absolute all along the x-axis, all along the y-axis. Now, where does it peak out? Notice it's going to peak out at 1. In this picture, it's right along this ridge, right? All of those points, okay, have a maximum here. And notice that is above this curve in the xy plane. That's where x times y is equal to 2. So if you track that curve in the xy plane, you get a bigger curve than this. But a little piece of that curve that goes through this square region, this rectangular piece of that is like this, the xy plane. And so above that, above this curve in the xy plane, that's where the surface hits a maximum. So you get absolute maximum everywhere x times y is equal to 2. That's a whole. Now, if you weren't looking at the picture, how would you, if you weren't really looking at the picture, how else would you go about looking at those minimum and maximum? But you can use kind of the same logic. kind of the same logic. Said, well, sleep. X is 0, Y is 0. Sine of x, y is then 0, or if x is pi and y is 1, sine of x, y is also 0. But another thing you might do is take the derivative, right? Okay, take the partial derivatives. So, what does the partial derivative of this function look like? What's the partial with respect to x there? So, yeah, what's the derivative of? Yeah, y times cosine of xy. Perfect, right? Okay. If you take the derivative with respect to x, right? Okay. Of course, the derivative of sine is just cosine, but when you're taking the derivative with respect to x, you have to apply the chain rule, right? So you have to take the derivative of xy and multiply it in, but with respect to x, that's just going to be y. What about f sub y, the partial derivative with respect to y? Well, it looks very similar to this, right? Don't you have x times cosine x y, right? And what do you want to do with those two things? Set them to 0, right? Okay. Oh boy, when is that going to be? At what now? When x times y is pi over 2, that's right, okay? So when x times y is pi over 2, you're exactly right, Elijah. This is going to be solutions to this equation, right? Okay, because cosine of pi over 2 is what? 0, okay? Yes, and where's the other solutions? Not x or y. Yes, right. Okay. So the other critical point is 0, 0, actually. 0, 0. Oh, so that's kind of interesting. So we get all of these points, or all of these points on this curve where x times y equal pi over 2, those are all critical points. But the only other critical point is at the origin. So these points along the axes don't really count as critical points, but they turn out to be absolute maximum, right? Okay, that's the only other critical. Okay? So let me move this down and fill that in. So critical points when x times y is pi over 2, or when both x and y are 0, right? Okay, that happens, of course, at the origin. So let's see. Let's just to fill it in here for completeness. So we have absolute max, right? Um, when x times y is equal to pi over 2, right? Um, right along that curve, or right above that curve, we should say. Let's try one more example of extrema, and then we can finally get back to integration. So this looks like a word problem from calculus. So you've seen problems like this one before, but we're just going to translate it to 3 dimensions. Okay. So it says a rectangular box is resting on the XY plane, and one corner of the box is at the origin, and the diametrically opposite corner is on the plane with this equation. So really need to see a picture of that to understand that one. So here's the picture of it. So we have a box. So that's this gray box here. And it's so it's resting on the XY plane, right? So the bottom is sitting on the XY plane, and one corner of the box is right here at the diametric corner, right? Diametrical is touching this plane. So this yellow surface in picture is that equation. And so not what the question is. Maybe I erased it, but you can imagine what the question is. Can y'all think of what the question is going to be? Yeah, I did erase the question. Oh, no, it's there. Okay. Find the maximum volume at box. Right. So if we construct a box as described there, okay, how would we locate this point? That's the variable here. How would we locate this point to get maximum volume? So see this point, this corner of the box has to go to the bottom of the box has to be the head of the box. But the bottom of the box is sitting on the XY plane. The only thing you can put a change here is the location of this diametric where you plot, but it's got to be on this yellow surface. It's got to touch this yellow surface. Okay. So of course you could put this point way up here, but then sort of possible. Wouldn't have any ball. That's right. Yeah, your box would essentially just be the z-axis, right? Okay, so it wouldn't have any volume. It would have volume 0. Or if you put this point here, I think the same thing happens, right? You get volume 0. Right? Okay, so these 3 points are not really candidates, but maximum. So this looks like a much better choice, whatever that point happens to be, right? But maybe we need to shift that up or over a little bit, right? Okay. Same thing here. If you this point, this edge is on the surface, you still get a flat box of 0. Right? So you want the score to be a little bit above the XY plane, right? Okay. But again, it's got to touch this surface. So how do we hack this thing? I already forgot the question, so I'm going to. So I turn. So what are the so what that is a box maximum? Yeah, box, right? It's not a rectangle, but it's a rectangular box. Right. Maximum volume. Yeah, that's what. So so you have lots of places, but out of those infinite places, should be looking backward. Maximum. Well, I think first things first, we're going to have to write down a formula for volume. Okay, because that's what we have to maximize. So I've got to write down how to get the volume given where we put back, right? And so let's see. What would the volume look like? So what would be a formula for the? So let's look at this picture, imagining that our is right there. So of course, how do you compute the volume of the box? This is going to be important later in this later today, maybe if we get to it. How do you compute the volume of a box? Yeah, that's right. It's length times width times height, right? So let's start with this dimension. I guess we can call that the length there. So what is that? That's the coordinate along the y-axis, right? So that's we're calling that y, right? So So we get y, and then we have this length right here. So of course, what's that? X. Let me put the x in front of the y just to keep our variables in alphabet expression. And then times what? Times the height, right? Which is z. Yeah. Okay. Right. So all right. So that all seems easy enough. But look, this is going to be hard for me to work with because this is a function of three variables, right? The volume here is written as a function of three variables. Now, we haven't been studying very closely functions of three variables, right? But we have been studying functions of two variables. So I'd like to get rid of one of the variables. The good candidate to get rid of here is z, because I have the equation for this plane, right? Because remember, this point has to fall on that plane, right? So the point xyz also has to satisfy this equation, because this point is supposed to fall on this yellow surface, which has this equation. Now, if you take that equation and solve it for z, you get this expression, right? So we know what the z value has to be, what the z coordinate has to be in terms of x and y. So instead of writing z here, I can write x times y times all of this, 8 minus 2x minus 4/3 y. Oh, now that's looking nicer, okay? That's looking better because that now is a function of two variables, just x and y. So we have the volume here written as a function of two variables. And I know how to find minima and maxima for functions, right, of two variables, right? Okay. So what thing am I going to do first? I'm going to compute partial derivatives. That's right. Okay. So let's, you want to expand that product first? So what is this? 8xy minus 2x squared y minus 4/3 xy squared. Did I do? Now we can't mess that up, or we'll be here all day. So is that correct? Yeah. All right. Now let's find the partial derivatives. So let's take the partial derivative with respect to x. Okay. Let's take the partial derivative with respect to x, and see what's that going to be. I think I can do that. Let's see. That's what, 8y, right? And then here, what, minus 4xy, and then there, not too bad. That's minus 4/3 y squared, right? And of course, what are we going to do with that? Set it to 0. Yay, that's right. Okay. So we're going to set that to 0. Okay. And now also take the partial with respect to y, correct? So we get what? 8x then what else here? Minus what? Minus 2x squared, right? Okay. And then what else there? Minus 8/3 xy. And then remember, we're going to set that to 0 also. Okay. So now we just want to find simultaneous solutions, right? To it looks terrible, but maybe not so bad. See if we can think about it. From that first equation, the partial with respect to x equals 0. Let's do a little factoring. So you can factor out of that all terms there. What can we factor out? You can factor out y, and from the coefficients also, you can also factor something out, right? 4, and that leaves us with 4y times what? 2 minus Is that X? And then here, one-third Y. And then from this one, we can factor something else also out, right? An X for sure, right? But also a 2. We can factor a 2 out at least. Wish we could factor more than a 2, but just a 2 there. So we get what? 4 minus what? Is that X again? Am I doing that right? And then here we factor out the 2, so that's minus 4/3 Y equal 0. All right, so can y'all start to see things here? How do y'all suggest here? Well, we're just looking for critical points now, right? We'll come back and decide if that's really a point that we're interested in, right? Okay, so hmm? See here you have a product that equals 0, right? Okay, so so you get 4Y equals 0, or all of this is equal to 0, right? And here you have 2X equals 0, or all of this is equal to 0. Aha. Okay. So look, that looks like now a second set of simultaneous equations, right? I want to pick X and Y so that both of these things are 0, because if both of these things are, if both this quantity and this quantity are 0, that means these two original equations will be 0 as well, right? So maybe this will lead us to an interesting critical point, right? Do y'all think y'all can, now, do you think you can solve this simultaneous equation? Oh, well, all right. So Robert, what do you suggest doing there? Oh, you want to get okay. You want to get rid of the fractions first. Okay. All right. That's a good instinct. All right. I wasn't thinking of that, but I was going to be a little bit more direct. But let's get rid of the fractions. So let's multiply everything by 3. So that gives me what? 6 minus 3x minus y equals 0. Is that right? And then here 12 minus 3x minus 4y equals 0. Okay, now what? There you go. Multiply one of them by multiply one of the equations by -1. Let's try the second one. So get a minus here, plus here, right? Of course, minus times 0 is still 0. So, and now just add the two equations together, because the x's will drop out if you do that. Okay, and so you would get what? -6, and then what? Plus 3y is equal to 0. And that means, what does that mean there? Y is equal to 2. Oh, thank God. Okay, so there we have y is equal to 2. And if y is equal to 2, what's x going to be equal to? Let's use this equation. So you would have 6 minus 3x minus 2 is equal to 0. So that looks to me like 3x is equal to 4, or x is 4/3. Aha! I'm now thinking that point is what? 4/3 and 2, and what we get when we plug 4/3 and 2 back into the original volume formula, right? Okay, not into the original volume formula, I'm sorry. What we get when we plug 4/3 and 2 back into this equation to find the z value, right? What would that give us? Z is equal to 8 minus 2 times 4/3 minus 4/3 times 2. So that looks like 8 minus, is that 16/3? So is it 8/3? Ah, so z value here, 8/3. So there's one of the critical points. That must be the correct one, right? That must be the one that leads to maximum volume. Because where are your other critical points going to happen? Yeah, only at the origin, right? The only other critical point there, right? Okay. It would have to be x and y both both x and y 0, right? Okay. To get yeah, okay. But that cannot be the maximum volume, right? So it looks like our maximum volume will happen is 8/3, and it happens when x is 4/3 and y is 2 there. Okay. All right. So there's an applied problem also. It's a function of 2. Okay, let's take a break here now. So we finished our extrema examples, and let's let's take a few minutes here until about 12:35 or something, and then we're going to come back and continue talking about integration. All right, so we're kind of done with differentiation for a while, and now we're going to do kind of the opposite of differentiation, right? Integration, but it does look a lot different in 3D space than it does in two-dimensional space. Okay. Oops, forgot to. Okay, I'm going to put the roll here and back. Okay, let's start again. Let me say one more thing about this problem. That critical point where x is 0 and y is 0, that doesn't correspond to the origin. That corresponds to this point on the graph, because when x is 0 and y is 0, z must be 8. If you plug 0 and 0 back into the original formula for the plane, you get z is equal to 8. So this is actually the minimum according to calculus, and then this point indeed is where this is where the volume would be minimum, and indeed that point would give you a volume of 0, and this is where the volume would be maximum indeed. However, these 2 points also are on these 2 points are also on the surface of the plane, and they would also give you volume of 0 as well. Okay, but when you actually use the partial derivatives, you get this point as the minimum volume, that point corresponding to the minimum volume. All right. I have another example, but we'll skip that one. in the notes. So remember last time we were looking at double integrals or iterated integrals, and we had done a couple of examples. This is the last, here's the last example that we did, okay? And remember, so these are going to be definite integrals that we're calculating, not indefinite integrals. But it's sort of like doing partial differentiation. When we're doing the integration, we're going to integrate with respect to one of the variables, but hold the other variable constant. Okay, so that's what we did in this example that we'd already worked out. This was before the test, so you probably forgot this example. So what this double or iterated integral means is going to first compute that inside definite integral, but as we have dy here, but we're thinking of y as being variable, so we're thinking of x as being a constant, right? Okay, so we're going to integrate first with respect to y, and that leaves us with this expression. Notice that because x is a constant, integrate with respect to y, you can use x as a limit of integration that definitely with respect to y. See, x really plays the role of constant. So when you compute this definite integration, inside definite up with 2x cubed minus x plus minus 1, that example. Since that's a function of x, notice then that you can in turn add respect to x. So that's what we did. Okay? Seeing these limits of integration. And so when we integrated with respect to x, that was just using anti-power loop, integrated, plug in the limits of integration, and then okay. So and using the anti-power loop, find the antiderivative and plug in 1 and 2, the limits of integration into the simplify. So in this example, all of this was just a kind of algebraic process or a calculus process. We didn't try to explain what that double might represent, okay, what value that would have to us, right? But just pointing out that, well, we carry out the simplification, right? We carry out the integration, you know, as a result, but what value the result has discussed it. I want to point out now that so we're going to start attaching meaning to that. We're going to start attaching meaning to that definite integral value that we got here, 5. Now, the way we're going to start doing this is first, I want to point out that the limits of integration on your course, you can think of those as defining a region in the XY plane. Okay, let me show you how you can use those limits of integration to create a region in the XY plane. Notice on that interior, like inside inner, since y is the variable, like we're thinking of y there as running from 1 to x. Okay, so what I'm going to do is set up an equation here like this and plot these two equations in the xy plane. See, I'm thinking of, since y is my variable integration, I'm thinking here of a y as running from 1 right up to x in the definite integral. So I'm going to plot this equation, y equals x and y equals 1 in the xy plane. Well, those are easy equations to plot, right? In the xy plane, okay? So here is y equals 1. Here is y equals x. And remember, we're thinking of letting the y values range from 1 to x. because those were so if you think of letting y be between 1 and x, that means what region of the xy, so that's in, right? It's inequality. So what region of the xy plane are we? It's only between y equals 1 and y equals x. So notice that's going to be everything below this line. That's the line y equals x, right? So everything below this 45 line down to that horizontal line y equals 1. So notice you get this piece of the xy plane, okay? This big wedge here of the xy plane. All of this. But those were just the inner limits of integration, okay? Those were just the inner limits of integration, because when we did the second integral, right, the outside integral, we also had limits of integration there as well. Now, here we're integrating with respect to x, right? So in this integral, you're thinking of letting x range between 1 and 2. So again, if you set up sort of little miniature equations here, x equal 2 and x equal 1, and graph them in the xy plane, notice, well, those are horizontal lines, right? So there's the line x equals 1, and there's the line x equals 2, right? So in other words, x has to always fall between 1 and 2. Well, where is x between 1 and 2? Well, it's between these two horizontal lines, right? Let me extend this horizontal line up. A vertical line, right? Okay. So let me extend that vertical line up. Okay. So you get here just this strip, right? This vertical strip between x equal 1 and x equal 2. So where do these two regions overlap? This original piece here, and then the piece where x is between 1 and 2. It's in this little wedge right here, right? That little colored wedge. So this part we're going to cut off. Let me, this part we're going to cut off. So let me erase that. So that region that was defined by the limits of integration, we're going to call that the region of integration for that double integral, right? Now, again, I explain what's the significance of that region of integration. You know, what does that mean other than there's a picture of it, right? Okay. What's that telling us, or what are we supposed to do with that? Well, we haven't gotten to that quite yet. All right. But we're approaching that. Let's try another one here. So there we have another double integral one. This one looks more formidable, but maybe it's not. Okay. All right. Actually compute. And so we want to evaluate this double integral, and then we want to plot what's called the region of integration for this. Okay. Never mind what that region of integration means. Okay. Just fine. Now, notice here, order of integration has been switched, right? From the previous example, you can reverse the order of integration. Nothing special about my first and second or vice versa. So in this example, integrating first with respect to x, and then second with respect to y. So so notice that, right? This first integral, we're going to integrate with respect to x, right? And then the second will integrate with respect to y. Now, because we're integrating that inner integral with respect to x, notice that these limits of integration make sense, right? Because y is just a constant with respect to x, right? So these limits of integration are really, for this inner integral, they're really just constants. Of course, for the outer integral, where we're integrating with respect to y, we also want constants as our limits of integration, right? See, there we have those two constants, right? As your limits of. All right, y'all think y'all can You know, do that integral, I don't know how hard. Remember, y is a constant, right? Not a variable. So when you're integrating with respect to x and you want to find the antiderivative, make this unnecessarily, right? Y is just a constant. They'll do that and you're going to end up with a expression with variables in it, right? Because the limits of the expression have variables. Okay. So integrate with respect to x and plug in your limits of integration, right? And take the difference. That's what we always do. But like you're doing a definite find the antiderivative by the plug in integration. Let's see what we get. Oh, that might be kind of messy. So try that. Um, this is important practice now because you're doing this a lot. Get really fast at it. You know, X is so I'm going to add, it were just three others. Okay, you forgot your finding your anger. That's the integrated. All right, so think of it as three. Doesn't matter. Find is constant. Yeah. Oh, you're this. You want to So that's right. Okay, all right. So some of you are a little bit rusty on your antiderivatives. Um, so you're gonna have to get some of the cobwebs out there, right? Okay, because we are going to be integrating quite a bit. All right. So for that inner integral, right, we're integrating with respect to x. So this is just a constant. You can think of that as just being the 3, right? Okay. So what's the antiderivative of a constant? That's the easiest antiderivative to find. That would just be what? You would just add the x, right? Okay. Yeah. So this antiderivative is, let me write it down here. So this antiderivative is just 3xy, right? But you have to, of course, evaluate it at you have to evaluate at your limits of integration. So you have 3y squared minus 6y, and then it's messier to write down actually than it is to do. Okay. So you have to evaluate it at the limits of integration. And don't forget, all of this exists inside of this second integral, which is being integrated with respect to y, right? Okay. So you get a lot of messy notation there, but this is truly a case where it's easier done than it is written down, right? All right, so what do? We plug in our limits of integration right here for x, correct? So, and then take the difference. So we're going to get, well, when you plug in that top limit of integration, right, it looks like what? 3 times 2y minus y squared, right? But don't forget you've got that extra y here. And then you have to subtract off when you plug in that second limit of integration, right? Okay. So that is what 3 times 3y squared minus 6y, right? And then don't forget that extra y is in there. You have to take the difference of those two expressions. And then after all that's done, we have to turn around and integrate that with respect to y, correct? All right, so what does all that simplify to? Now tell me, so if you multiply the y through here, multiply the y through here, and then take the difference. Don't forget you have to multiply it into 3 also, right? And then take the difference of those two expressions. What does that all simplify to? That's just a nice polynomial. Those are just nice polynomial expressions. So it is going to, some like terms are going to combine, right? What do you end up with there? Yeah, 24y squared minus, is that what other people got there? Can we get some agreement on that? Yeah, right. And remember, now we're integrating that with respect to y. Oh, finally now, this looks more like a more typical calculus 1 definite integral. Okay. So This is something that might have been on your assignment. That's straightforward. Definite integral, and we can integrate that now, or we can find the antiderivative of the integral here, right? Okay, of the integrand. We can find the antiderivative by using the anti-power rule, right? So we would get what do we get there? 24 over, let's say 24 times y cubed over 3, right? Minus 12 times y to the 4th over 4. That's what I call the anti-power rule, because that's just the opposite of the power rule for differentiation, right? And then, but we want to evaluate that at our limits of integration, right? Remember, you don't need the constant here because we're doing definite integration. So the constant isn't needed, okay? Oh, wow. Well, I can do one of those. I think if we plug 0 in, right, that's going to be 0, right? Okay. And what happens when we plug 2 in? That's a little bit harder. So we get 24 times 2 cubed over 3 minus 12 times 2 to the 4th power over 4, right? That's what we get when you plug 2 in. Of course, when you plug 0 in, both terms will just disappear, so you just get 0. So what does all this work out to? That's what 64 minus 48, which is that 36 or 16? 16, yeah. I'm going crazy. So 16. So there's that number 16. Now again, what does that mean? We're so, at this point we don't know, right? But that is the correct value for that iterated or double integral. Now, what does the region of integration for this double integral look like? Okay, all right. So remember, you use your boundaries of integration, right? They will define a region in XY plane. Now, these limits of integration, though, are a little bit difficult, right? So since you're integrating first with respect to x, set up these two equations, okay? See, this inner integral means we're going to let x range between 6y squared minus, 3y squared minus 6y and 2y squared, 2y minus y squared. So set those limits of integration to x, and then try to plot those two equations. Okay, try to plot them. Wow, right? If you think of those equations just right, though, you can plot them. Okay, that top equation, that top limit of integration, that's just a parabola. Okay, because you have y squared and 2y. So that's really just the graph of a parabola, except you're used to saying y x squared. That's the graph of parabola, but this is reversed. This is x equals y squared. So you have a parabola that's opening to the left, to the right, not up and down. But if you sort of shift your perspective, instead of up and down, to left to right, figure out what that parabola looks like. Which way does that one? 2y minus y squared. Notice it's minus y squared, right? Down, but left to right here. Okay, it's x. So what's the, well, to which side? Yeah, I think it's going to open to okay. So the left, right, down the x-axis, right? Okay, and then the other one, since you have y squared to the left. So you're going to have a parabola opening to the left and a parabola opening to the right. Notice that's going to enclose a region. So see, we're getting close there to going to get closer to our region of integration. All right, let's see if we can figure out what those. Let's see if we can figure out what those parabolas are. So this first one, x equals 2y minus y squared. How do y'all want to graph that one? One thing you might look for are the y-intercepts. That might be helpful. How would you find the y-intercepts here? Set what to 0? The y-intercepts, where it crosses the y-axis. Set x to 0, right. So set x to 0. If you set x to 0, oh, that now is a little bit easier to deal with, right? Isn't that going to be y times 2 minus y equals 0? And I think I know what the solutions to that are, right? Aren't they 0 and 2? Yay! Okay. So this first one crosses this equation, crosses the y-axis at 0 and 2. Let me plot that here. So this is obviously 0. Let's make 2 up there. So I'll make 2 blocks there be 1 instead of 1 block. 1. All right, so this is 2 on the y-axis. And we already said, which way do we think that one opens? To the left. So I'm going to get a parabola, right, Ian? I think I'm going to get a parabola that looks something like this, okay, opening to the left. But I really need to know this point over here, right? How far does that extend to the right on the x-axis? You know what that point is called? That's called the vertex, right? That is the vertex. You know how to find the vertex there? The y-coordinate is what? How do you know that? Oh, the mean of 0 and 2. Oh, so, Robert's got a really good idea there, right? This is symmetric, right? This parabola is symmetric. So that means you know that the vertex has to be here at, y equals 1. Oh, I like that idea. Okay. So you know y is equal to 1. If I know y is equal to 1, then, Robert, I think I've got it, don't I? If y is equal to 1, then what's x equal to? 2 times 1 minus 1 squared is 1. Yay! Okay. All right. So, so that must be my vertex. I almost hit it here, but not quite. So let's redraw this. That's very good, Robert. Right there, 1 and 1. That is the vertex of this parabola, one that opens this way. What about the other one then? What about that lower bound? So can we find its intercepts as well? Are they going to be the same? Be nice if they were. So let's set that 0 is equal to 3y squared minus 6y. So 0 is equal to 3y times y minus 2. Yep. So same intercepts for this parabola. And so we know this is the one opening to the right, right? So we know its vertex also must be at y equals 1. And when you plug y equal 1 in here into this equation, what do we get? We get x is equal to 3 times 1 squared minus 6 times 1. Is that minus 3? So down here is the vertex for that second parabola. Nice. So it opens like this. So where do y'all think your region of integration is? Again, whatever that means. Remember, you're going to let x, right? I'm sorry. Yeah. I'm not sorry. It's correct, right? You're letting x run what? Between these two curves, right? From this curve on the left to this curve on the right. So isn't that going to give us between these two curves like this? Yeah. Now we have to make sure that this also matches up with the outer limits of integration, which say that y has to range between 0 and 2. In this region, does y range between 0 and 2? Yeah, I think it does, right? Just because of those intercepts, okay? So we've got it. There's our region of integration for that particular. Sorry. Now, here's one application now of our double integrals and our region of integration. So I want you to think back now to calculus 1. Suppose you were presented with this problem. So you want to find the area between these two functions, between these two curves, right? So that shaded area. Remember how you did this in calculus 1? The idea was really straightforward, okay? So tell me that, David, what you said. Let's write it down notationally, right? Okay. Yeah, integral, right? The first function, so you mean the top function? G sub 2. Yeah, okay. Oh, I see. Oh, so you combined them. Okay. Yeah. I was going to write, I thought what you were going to say was this. Find first the definite integral from a to b of the top function. So here would be the definite integral a to b of that top function. By the way, what does that represent geometrically? What does that definite integral mean? Yeah, that would mean the area beneath this curve down to the x-axis, right? So beneath this curve down to the x-axis, that would include all of this, correct? But in the area we want, right, we don't want this dark part, correct? We just want the striped part above. So how do you get rid of the dark part? You subtract it out, correct? So what is that area? Well, that's the area beneath the lower curve, right? So that looks like this as a definite integral, right? So you take the difference of the two definite. This one gives you this lower area, right? This one gives you the area beneath the first curve. So when you take the area beneath the top curve minus this lower area, that gives you the area between the two curves, right? So you can calculate that area this way. But because of the nice properties of integration, you can really combine those two integrals into one integral. So this is what you were suggesting, David. Okay, yeah. You can take those two separate integrals and you can combine them into one integral. It's right, just one definite integral difference of two. However, this and this iterated. Okay. So this is an iterated integral. Can y'all see how to write that as integrated integral? It's going to look like this. So I came that definite integral that gives you the area between those two curves, right? Okay, is the same as this double iterated. Now, why are those two things the same? It's easy to check the same. Okay. Guys, how would you evaluate this? How would you evaluate this double? So what do? Start first on the inside, right? What is the integrand function on the inside, though? So what's the integrand here? What is the function of the expression that you're integrating here? It's not the dy. So what is it? It's 1, right? Okay. That's just, it looks the invisible, right? But it's really there. It's 1. So you're just integrating the constant 1 with respect to y. Okay. Of course, when you integrate that with respect to y, what do you get? What now? Yeah, when you integrate, what are y'all saying? Yeah, when you integrate 1 with respect to y, what's the antiderivative? What? Y, right, it's y, correct, right? Y to the first power. And then, of course, you have to evaluate that at your limits of integration, right? Which are g sub 1x and g sub 2x. But those are so easy, right, to plug in. You just plug them in and take the difference. And notice what you get when you plug them in and take the difference. You just get what? Well, what we have here, right? G sub 2x minus g sub 1x. And of course, that's the area between the. So this double integral also gives you the area between the two regions. But notice what the integrand is. It's simple. It's just what? 1, right? Okay. So when you integrate the 1 here, right, you get also the area between those two regions. Now, what is your region of integration? So if you made a picture of your region of integration, what would your region of integration look like? It would look like this, wouldn't it? Okay, right? Because you're integrating x from where to where? A to B, right? So along the x-axis, you're starting at A and stopping at B. Along the y-axis, though, where are you starting at and stopping at, according to that double integral? You're starting at G1 on the bottom, right, and going up to what? G2, right? Exactly this picture, okay? Oh, so wait. So what's the moral of, we're running out of time. What's the moral of the story there? You can find area of a region, right? Okay, by giving a double integral, right? Where your region of integration is that area, but what function are you integrating? 1, right? Okay, right. Oh, well, there's our first application of double integrals. Okay, another way of computing area of a region in the xy plane. Now, unfortunately, that's not a very exciting application because we already know how to do that. We already know how to do that. Okay, so that application seems a little bit tricky. So we need to find some other reason to justify double other things. But this is our first application. Double. Okay, all right. So I'm sorry, I'm out of time. So I'll see you guys on Monday. Wow, it's like I hardly see y'all anymore. And that one homework that's due tonight, I'm going to delay it a little bit, like I mentioned. So look for the new due date.